In this video, we're going to be talking more about process models, specifically the process model that's recommended by our textbook authors. This is sort of a combination of Agile concepts with that evolutionary spiral model that we've seen before. They call this the Agile spiral model. And this really gets into how you can adopt and sort of add different components from different process models to tailor one that really fits you, your team, and your organization. We'll also be taking a look at some of the common tasks that you might encounter as you go through the different activities in the process model. And then lastly, we'll be taking a little bit of a look at the maintenance activity. Without further ado, let's get into it. So as we've talked about, every serious software project needs some sort of generic software process to follow or build on. But every project's a little bit different, and every team's a little bit different. Every organization has its own goals and objectives and ways of doing things. So no single software process or software engineering framework is going to be appropriate for every single software product or every single team. So any software process is going to have to be adapted to the needs of the developers and stakeholders and tailored to fit the current project and its team members and the user's needs. So what we're really going to be getting into in these slides and chapter 4 of your textbook is how one of these software processes can be adopted to meet the needs of a team. In this case, the textbook authors are taking the spiral, that's that prescriptive method, and they're going to be adding in some ideas from the Agile methodology to sort of get the best of both worlds. And this is the recommended process that at least the textbook recommends. It's also based on some principles from a paper entitled Review of Myths on Original Development Model. I'll leave how to pronounce that author's name as an exercise to the reader. So now let's take a look at some of those principles. And these are all principles for organizing software projects at a high level. The first principle is it's risky to use a linear process model without ample feedback. One of the most famous examples of a linear process model, which we've already talked about a little bit, is the waterfall model. And in that case, a lot of the risk comes from the inability to change and the risk from not involving the stakeholders enough. We only involve them in the communication and the deployment phase. That means we could go the whole project without seeing them since the start until we get to the end, which is a big problem if some of the requirements changed. The second principle is that it's never possible nor desirable to plan big upfront requirements gathering. The reason why it's not desirable is you're going to put all that time into requirements gathering up front, all that cost associated with it, and they'll likely change later on. And this ties into point number 3. Upfront requirements gathering may not reduce costs or even prevent time slippage. And that again is due to change. Number 4 is appropriate project management is integral to software development. Number 5 is documents should evolve with the software and should not delay the start of construction. So again, that's getting into the idea that we're sort of going in cycles, working on the planning, the modeling, the construction, and then back to them. So there should be some way to feedback or sort of go back and update the documents so that they evolve with the software. Number 6 is involve stakeholders early and frequently in the development process. That feedback from stakeholders is key so that we can manage change effectively. And the last point, number 7, is testers need to become involved in the process prior to software construction. So ideally, we want test-driven development, which means that we even create the tests before the code's even written. But we also want to have testing throughout the whole process, not just at the end, which we kind of see in the V model and the waterfall model. So the recommended process model, like I said, is going to be a hybrid of the Agile and the spiral model. So the idea is to add Agile into every cycle of the spiral model to sort of break it away from that prescriptive side of things. So what we see on screen right now is a version of the spiral model that's sort of adapted for prototype development. Still not an Agile version, but it's one that's more focused on prototypes. And I'll just review how the spiral model works. So we start off in the center of the spiral in the determine objectives phase. This would be sort of things like requirements gathering. You then continue on through identifying risks, that'd be any potential problems, and plan out solutions for them. Next, you plan out the next iteration of the prototype or the software you're going to create. Right now, we're just starting out, so this would be the first iteration. Then you do the construction, the development, and the testing, and you produce that prototype. And then you present it back to the stakeholders, get their feedback, and you have to determine the objectives, the requirements, how they've changed since then, and what they like about the prototype, what they don't like about the prototype, as we're going to use that to continue on with the process. So again, we start by identifying risks. What are the potential problems? Does it make sense to keep going on? We plan the next iteration. What are we going to add to the prototype? We construct the next prototype. And then we get the feedback again from the stakeholders. And it keeps going on and on like this, with the prototype getting more complete, more complex as we go on and outwards from the spiral. So again, just to review a little bit, some characteristics of an agile methodology versus an evolutionary model. Remember that spiral is an evolutionary prescriptive model. So for agile, it's not suitable for large, high-risk, or mission-critical projects. It's also, agile tends to be better for small teams. Number two, minimal rules and minimal documentation. Agile is a lightweight methodology, means we only want documentation when it's actually going to be used, when it's necessary. Number three, we want continuous involvement of testers for easy to accommodate project changes. That's the whole driver behind Agile. Number five, depends heavily on stakeholder interaction. 6, easy to manage. We want lightweight management. Usually teams are self-organizing, self-managing. 7, early delivery of partial solution. Those are those prototypes. Number 8, informal risk management. That one's not necessarily a great thing if we're worried about risk. And 9, built-in continuous process improvement. So we have that process for improving. For example, in Scrum, we have that sprint review where we look back and see how the process could be improved. Now, when we're talking about the spiral evolutionary model, it's not suitable for small, low-risk projects, but it does do well for large, more high-risk projects. So we have the risk management built in, and it's designed for sort of bigger teams. Number 2, several steps required, along with documentation done up front. Sort of different than Agile, where the documentation is lightweight. 3, early involvement of testers. 4, hard to accommodate project changes until the prototype is complete. And number 5, continuous stakeholder involvement in planning and risk assessment. Number 6, requires formal project management and coordination. Number 7, product and not always obvious. We don't know when we're actually done in that spiral, but it does have good risk management. And again, it has process improvement handled at end of project. So what the textbook's trying to do is sort of combine these two to get the best of both worlds. So we want a method that's going to work for both the small and large projects, still focusing on a small team because it'll be agile. And we want to get the earlier development, lighter documentation, and sort of get rid of all the cons of both. So here we see on the screen the agile spiral model. This is that adapted spiral model that the textbook recommends. Looks a little bit complicated here, but you can sort of see the spiral in the flow, where there's a loop that keeps going. And we'll be going through each one of these points just to make everything. So the first stage after the project conception is the requirements engineering or requirements definition activity, highlighted here. So in requirements definition, there's a few key things. Number 1, we have to encourage active stakeholder participation by matching their availability and valuing their input. Number 2, we use simple models, for example, post-it notes, fast sketches, user stories, to reduce barriers to participation. And this is sort of the fault of some other models, sort of like the unified model, is that if we make really complex documentation in regards to requirements, it might be great for the dev team or people that are familiar with the development process, but it's going to be hard for your stakeholders to understand and be able to process that. So we really want to reduce those barriers to participation. One thing that you should have done by now is tried writing a user story, and you can see how simple that is with just filling in those blanks. That makes it really accessible to any kind of stakeholder. And number 3 sort of ties into this, which is take time to explain your requirements representation techniques before using them. Everyone on your team should understand what they mean and what they represent, as well as your stakeholders. After all, the stakeholders are the ones that's going to be evaluating your output at the end, so they should have a good understanding of at least what the requirements are. Number 4 is adopt stakeholder terminology and avoid technical jargon. So whenever possible, you want to be using the same terminology as the stakeholder. This makes communication easier and more effective. Number 5 is use a breadth-first approach to get the big picture of the project before getting too bogged down into details. So when you're gathering the requirements, it's important to go for breadth. You want to understand the requirements at a high level, rather than getting too caught up into the details. The details can be figured out more just in time when you actually start getting to construction or planning and modeling. And that's just what point number 6 is. Developers and stakeholders refine requirements just in time as user stories are ready to be implemented. So we don't need to have the exact details, like when we were writing that user story about adding those bookmarks. We didn't have to have the exact details. We didn't need to know what sort of data structure those bookmarks are being held in or anything like that. We just needed the sort of high level idea of what the user wanted. Now we can sort of refine those requirements more just in time as we start actually implementing them. Though in reality, the stakeholder probably doesn't care about too fine details like the data structure you're using, as long as it fulfills the other requirements, including the non-functional ones like performance. So number 7, treat the list of features like a prioritized list and implement the most important user stories first. 8, collaborate closely with stakeholders and document requirements so they're useful to all when creating the next prototype. Number 9 is question the need to maintain models and documentation not referenced to in the future. So, like I was saying, Agile is a lightweight methodology. We want to minimize the amount of documentation. Documentation should be just sufficient to get us on to the next step. For acquiring documents and diagrams and things like that, and they're just going into a filing cabinet and no one's actually going to be looking at them at a later stage, there is no point into creating them. So we should really question why those are being created if we're not going to be referring to them in the future. And number 10 is a big one, is ensure management support for the stakeholders and resource availability during requirements definition. Management sort of pulls the rug, drops their support for the project halfway through, it's not going to end well, and the whole thing will be for naught. So before we even get started on the project, we need to make sure that there actually is support for it in the more longer term. Another thing I should point out is that stakeholders may not actually know what they want. They might not know what requirements they need up front. They might actually need to see the user stories they come up with implemented and running to know if it's correct or not, if what they specified is actually what they wanted. Again, this is why it's so important to have the incremental method with prototypes being developed, so you can actually put something in front of them so they can see, is this what I wanted? And how can it be changed to better fit what I wanted? So we really shouldn't expect our first set of requirements to be fully correct. So after requirements engineering, we then move on to design, specifically architectural design. So there's a few elements of Agile architectural design. This is specifically the design for the prototype. In this case, the first prototype, because we're still starting the cycle. And those are focus on key quality attributes and incorporate them into the prototype as they're constructed. Keep in mind that successful software products combine customer visible features and infrastructure needed to enable them. So the big thing there is our prototype should have two things. They should have features that are visible to the customer, like GUI. That's very easy for them to test and accept and interact with. But they also need to have the sort of supporting infrastructure and backend that actually drives those features. Agile architectures enable code maintainability and evolvability if attention is paid to architectural decisions and quality issues. So what we mean here by evolvability is that we want our code increments, our prototypes, to actually be something that we can build on in later cycles, not something we have to throw away. So that means while designing the architecture, we have to be thinking forward to the next stages of the project. So managing and synchronizing dependencies amongst functional and architectural requirements is needed to ensure evolving architecture will be ready for future increments. That's sort of what I'm getting into, but it also means that we have to keep sort of the other requirements and functional ones in mind, sort of like performance and things like that. We could implement a feature, but if it goes extremely slow, it's not going to be that much help to us. So next up is going to be estimate required project resources. And what when you're talking about project resources, The main thing we're talking about is time. How long is it going to complete this prototype? So with agile methods, it's usually pretty hard to estimate time, at least much more harder than the prescriptive models, which can have a predefined amount of time set for each activity. So teams should use historic data to develop an estimate of the number of days needed to complete each user story known at the start of the project. So in this case, historic data is mostly past projects, how long it took to complete them, how long it took to complete similar user stories in other projects. Number two is loosely organize the user stories into sets. They'll make up each sprint planned to complete a prototype. Notice here we're sort of getting some of the agile methodology of the XP method, which dealt with user stories and also sort of organized them into sets to be developed in the next sprint prototype. Number three, sum up the number of days to complete each sprint to provide an estimate for the duration of the total project. So that makes sense. You have a list of user stories, you know how many days each one's going to take to implement, you put them together based on what you're going to do in the next sprint, and then you sum them, and that gives you a rough idea of how long it will take. Of course, there's going to be other overhead like integration and things like that. Then, the key here is that you revise that estimate as requirements are added to the project, prototypes are delivered, and you start getting a better idea of how the team's functioning. So you can calculate a better velocity for the next sprint based on how the last one went. So now, after we have everything planned out and estimated, we can start working on constructing our first prototype. And we have a few guidelines for creating that first prototype. So the number one is transition from a paper prototype to a software design. So what's meant here by paper prototype are things like wireframes or GUI mockups that you might literally draw on paper. This is a great way of presenting sort of a potential graphical user interface to the stakeholders and have their approval or disapproval of that before you even write any code. After that's approved, you go to number two, prototype the user interface, sort of actually make that user interface in some programming language or software. And by doing this, you're sort of creating a virtual prototype. So it's something that runs, it has code, but it's really just the user interface, show the layout of things like that. It's not really taking any input or output or doing anything. Then number four, you want to add input and output to your prototype. So you want to actually register those buttons being clicked, menus pulled, things like that, opening files. And then you want to start engineering your algorithms to actually start processing this input to do something. Once that's complete, you then test your prototype, both unit tests and acceptance tests. And the last key guideline for prototyping is you want to prototype with development in mind. So that means don't take shortcuts. You might be pressured when you're getting close to deadlines and things like that to just sort of not put the best quality code in, just do whatever you can to get it working. But the problem with that approach is it's going to cause issues later on. Remember, this prototype's going to come back in the next sprint, and you're supposed to be building on it. If you had some garbage code in there, that means it's going to add more time to the next sprint, and it's all going to snowball from there. So when you're developing these prototypes, you want them to be something that you don't have to throw away or significantly refactor. You want them to be things that you can build on for the next sprint and keep building until they eventually become the real product at the end. So after we've constructed our prototype, we now have to evaluate that prototype. So this should be something that's done with the stakeholders because it's their evaluation that's really going to matter here. And instead of just giving the prototype to the stakeholders and saying, what do you think? We want to provide some scaffolding for asking for feedback. So we want to either like use a form or something like that to make the feedback more structured. A good model is sort of asking them to respond with what they like, what they wish the prototype had, and sort of what if. What if it had this feature? So you want some sort of scaffolding to make their feedback more structured and make it easier for them to provide feedback on key things that you're interested in. Next thing is test your prototype on the right people. So we don't want to just have developers testing the prototype because they're the ones that are working with the software every day. They're going to not be a good measure of, for example, usability because they know where everything is, they know exactly how it's laid out, and things like that. Sort of a good real life example of this is again in video game design. So, one problem with video game design, with the developers and even the QA testers, that because they are playing the game every day to test out the features while they're implementing it or testing it, they're doing the same thing in that game over and over and over again, that they sort of lose perspective and aren't able to judge how difficult the game is, for example, or how intuitive certain concepts in the game are, because they're doing it so much it's become second nature to them. So, one thing you should do when you're testing your prototype is actually test it with the end users, people that don't have that level of this is my job, I do this every day over and over again, test this. And that's for all types of software, not just video games. That's just an easy example. So, number three is asking the right questions. So, when you're showing a prototype to someone, you're sort of tempted to ask almost leading questions that are going to give you the answers you want. But those aren't necessarily the answers you need. You want to be asking questions that are actually going to help you develop the prototype. Sometimes those are tough questions to ask. And that sort of leads us into number four, is be neutral when presenting alternatives to the users. You don't want to push them into certain alternatives just because that's what you want, or you don't want to get rid of a feature that you spent time on when maybe that's not what they actually want. Might be good for you in the short term if they agree with you, but in the long term, if they're not actually developing what the stakeholder wants, it could be a problem at the end of the process. Number five is adapt while testing. So in some cases, if there's something that the stakeholder or the user who's testing the software doesn't like, it might be as simple as just changing a simple setting to fix that in the prototype. So if there's something that you can easily change right while they're testing it, you might as well do that while they're testing because you'll get a little bit more feedback there than having to wait a whole sprint for it to change. And number six, which is pretty obvious, is allow the user to contribute ideas. That means not just what they like or don't like, but also maybe suggestions for how the software could be better or new features that could be added. So after that first prototype is constructed and evaluated, we now have to make a big decision. This is the go or no go decision. And essentially what this is deciding if we're going to scrap the project and end it right away, or if it's worth investing more time and resources into it. This can be a really hard decision to make because from a developer's team's perspective, they put a lot of resources into it, a lot of personal effort, and it can be hard to decide to scrap it, even if that's what's in the best interest of the users and the company. And this sort of ties into something called the sunk cost fallacy, where because you've spent a lot of time or effort on something, it means you don't want to throw it out, even though that would be the best course of action. So, key here is making that decision. Is this worth continuing on or not? So, there's a few things to consider here. The first is that cost estimates and scheduled changes are proposed based on how that evaluation went with the prototype. Another thing here is managing risk. So, we have to consider risk of exceeding the budget and missing the delivery date. We have to assess that. What's the likelihood of that happening? We also have a big risk that we have to consider, which is failing to satisfy the user's expectations. Are we actually going to be able to make what the stakeholders want? And lastly, number four is to get or confirm the commitment from stakeholders and management to actually providing the resource we need to complete the next prototype. So, based on these four things, we then decide are we going to go on and continue making and evolving the software, or are we going to decide to scrap the project? So, if we decide to keep going, we now have to evolve that prototype. And this really comprises three different activities: evolve the system, redefine the scope, and then construct the next prototype. So, we'll talk a little bit about the evolution of prototypes. So, the big first step is to collect all feedback and data from the evaluations of the current prototype. We got a lot of that at that evaluation process. And then the developers and stakeholders begin negotiations to plan the creation of another prototype. And part of these negotiations would be what features or requirements are going to be included in the new prototype. Once that's agreed upon, consideration can be given to any known time and budget constraints, as well as the feasibility of actually implementing these things in the prototype within those constraints. If those risks are deemed acceptable, the work continues. And as I've said a few times now, we really need to design to allow for future changes. We want to build on that prototype, not throw them out, because that could be devastating in terms of cost, how long it's going to take. So we have to build that in with our design, is how we're going to build on this in the future. So after we construct a new prototype, we evaluate it again, and eventually, as we're going around this circle over and over again, one of two things are going to happen. It's going to get thrown out and the project's going to end, or the prototype is accepted completely with no more changes needed right away, and it can be considered to be the finished software product. In this case, the prototype becomes a software release. But before it's a release candidate. So release candidates are subject to user acceptance testing, in addition to testing conducted during the prototype construction. So user acceptance tests are based on acceptance criteria that were recorded as user stories were created. And we saw some examples of those in our activity for this week, where we created a user story for bookmarks, as well as some acceptance criteria for them. So those are going to be used on the release candidates to sort of ensure that they actually are fulfilling those user stories. So user feedback during acceptance testing is also encouraged. So these user acceptance tests are both automated as well as manual ones that involve actual end users. And these should really focus on user visible functions as portrayed via the user interface. Remember, user acceptance tests are from the user's perspective, so they tend to deal with front-end things, whereas unit testing and things like that are more of the programmer or the developer's perspective. And developers should make changes, but only if these are changes that will not delay the release of the prototype. If the big changes are required, it shouldn't be a release, rather it should go back into the prototyping phase. Changes aren't made, they need to be verified in a second round of acceptance testing before moving on. Be a big issue if you added new issues when you added those changes, and they got into the final product. So we have to test again. Generally, should always be testing after a change. The issues and lessons learned from creating the release candidate should be documented and considered. This is all part of that process of a continual improvement. So we want to not just make better software, but also make the process itself for making that software better. And that will lead also to better costs and time estimates for future projects. But software isn't done at this point. You don't just release software and you're done with it. You then have to enter the maintenance phase. So we haven't talked too much about software maintenance, but it can be divided into a few different categories. First of all, I'll just summarize what maintenance is. These are activities needed to keep software operational after it has been accepted and released in an end user environment. And these fall into these four categories here. The first is corrective maintenance, and this is reactive modification of software to repair problems discovered after the software has been delivered. Next is adaptive maintenance. This is reactive modifications of software after delivery to keep the software usable in a changing environment. Next is perfective maintenance. This is proactive modification of the software after delivery to provide new user features, better program code structure, or improved documentation. And then we have preventative maintenance. This is the proactive modification of software after delivery to correct product faults before discovery by users. So, in terms of maintenance, the one that you spend most of your time on will be preventative maintenance. That's going to be adding new features and making the program better. But in terms of correcting issues and dealing with bugs, you're mostly going to be doing adaptive and corrective maintenance. So that would be reactive to sort of users discovering bugs and things like that, and repairing problems. So preventative maintenance is more rarer, but it does occur. And this, like I said, with the proactive modification of software to correct for bugs that could happen in the future. Good example of this is the Y2K bug. So what the Y2K bug was is back in the 90s, there was a big concern that some systems, mostly Windows-based, were recording dates as 2 digits of the year. So like 1986 would be the number 86, 1995 would be the number 95. But there's a big problem with this. Once you get to 2000, it goes 00, which is indistinguishable from 1900. So there's a lot of concern that this would cause a lot of programs to fail. So a massive initiative had to be done to do a lot of preventative maintenance on a ton of different systems to make sure that they were all Y2K compliant or that they handled dates properly. Fortunately for most Unix systems, they handled dates differently. They instead handled dates as number of seconds since January 1st, 1970 at midnight UTC, so they didn't quite fall into that. Now, you might think that's pretty silly. How could we be so poorly forward thinking that we would store years as two digits? However, that probably isn't going to be the last big time related bug to happen. In fact, there's one on the horizon already called the year 2038 bug, or the Y2K 38 bug, or the apocalypse. And what this is the way I mentioned, is that Unix systems, or at least Unix date formats, store the time by number of seconds since January 1st, 1970, midnight UTC. The problem is, however, on 32-bit systems, there's only so many numbers you can hold in an unsigned integer. And it turns out that if you're using 32 bits to store a date, that's going to run out on January 19th, 2038 at 3 a.m., 14 minutes, and 7 seconds UTC. So that's about 16 years from now. Fortunately, most of our computers are moving on to 64-bit architectures, so for a lot of software, this has already been resolved, and a lot of efforts have already been made for preventative maintenance for the year 2038 problem. However, there are a lot of embedded systems out there. Remember, we talked a little bit about embedded systems. Those are sort of software running on hardware devices that you don't directly interact with, like maybe TV remote control, things like that are using 32-bit architectures or even less. They're still storing time in this way with 32 bits. So if those aren't corrected, and there's going to be a lot harder to correct those on embedded hardware in the next 15 years, we are going to have a bit of a problem. So it'll be interesting to see how that plays out. I know most of you probably weren't old enough to be too aware of the Y2K bug, but at the time it was quite a big deal. There's even like whole nationwide initiatives to deal with it, even people panicking and going into fallout shelters like that on New Year's because they were so afraid of it. So it will be interesting to see how everyone reacts to the 2038 problem. Is it even going to be a big deal? Will the news media even understand it enough to report on it? And we do still have 15 years to deal with it. So it'll be fairly interesting to see how that plays out. Anyway, that's all I have for you in this video. Thank you for watching, and have a great day.